wait, let me change that. Okay.
All right.
So are you seeing now the percent?
I think I still, okay. Gabriela, can you hear me?
Yes, I can hear you. Something quit on my end for a second.
Yeah.
This is not happening during the presentation. I have to see. Let me try again sharing. Okay, so and now.
Okay, I can see your screen.
I see the slides now.
Yes, now it's in a public mode. Yeah, exactly. Just
so full
your
screen.
slides only. Yeah.
Okay. Okay. Very good.
Maybe set. Right.
All good.
So let's give it a few minutes more. Let the audience together, and we will start in 2-3 minutes, maybe.
Sounds good.
It's very nice to see you. Eventually meet you, because I think a lot of colleagues of mine joined your group. So we had a lot of conversations about Zurich Power System Lab, but we never get to talk.
Or the other way around, right? Stefanos was he went actually back and forth now.
Yeah, back and forth indeed. Lesia Mitridati must work with you, right? So.
Well, she had her last day a week ago, and she's now with DTU. So she moved to.
Oh, back to DTU. Okay. Okay.
Exactly. Yeah.
So. Yeah. No? All right, I think I can slowly start introducing you, and then, the people will still gather. All right, welcome everyone to this final episode of an optimal seminar series devoted to learning optimization of energy systems. Today, it's our pleasure to host Gabriela Hug, who is a professor at Power System Laboratory at ETH Zürich. Gabriela, she received her master and Ph.D. degrees from the same university, and then she was working in Canada, in Toronto, in a special studies group of Hydro One. And then shortly after, she joined Carnegie Mellon University in Pittsburgh, where she was assistant professor from 2009 to 2015. And now she is with ETH Zürich. We know Gabriela thanks to numerous works of hers in her group, so at the very different interfaces of power systems research. So, and yeah, I will let Gabriela speak for herself. So I think we'll all get to see today. Just some on organizational side, I suggest to you folks to use a chat to drop your questions. I can translate them to Gabriela as we go, or maybe we can even make it more cozy. So feel free to unmute yourself and ask your questions directly as we go. Thank you, Gabriela, for joining us today. It's a great pleasure. Please, the floor is yours.
Okay, great. So thanks a lot for the invitation to present here. It's my pleasure to present some of our work on optimization and operation of converter-dominated power systems. So the talk is structured as follows. I will first give a short introduction, motivation for the topic. Then I will need some models in the next 3 parts of the presentations. I'm going to introduce these models there. And then I'm going to have 3 main parts, which all focus on different timescales for converter based systems, unit commitment in low inertia systems, then storage sizing for frequency control, so basically combining planning and operation, and then finally looking at some ways how we can do fast frequency control, looking at reinforcement learning and using as a benchmark an MPC approach, and finally some conclusions. So then let me start with the introduction or motivation. I think there are generally two major trends that are going on in electric power systems. One obviously is the increase in renewable generation from wind and solar power to replace either fossil fuels or nuclear power plants. Just to give some insights into the situation in Switzerland, we currently have about 60% hydropower, 30% nuclear, a little bit of thermal, and then wind and solar, another 5%, but that's about to increase because the goal is to get out of nuclear power and replace it with PV. Another major trend, which is not the focus of this talk today, is electrification, so the decarbonization of mobility and the heating sector via e-mobility and heat pumps, and that will likely lead to an increase in electric energy demand, so requiring additional resources to cover that demand. So the focus today is going to be on the renewable generation. This is not just, of course, a topic in Switzerland, but all over the world. We're increasing the capacities for PV and wind generation. And these are some figures taken from the Renewables 2021 Global Status Report, which clearly show that we do have an increase. We still have a long way to go, but a clear increase in inverter-based system or resources. Now, in terms of the characteristics of inverter-based resources, well, we're used to synchronous generators, and they have some natural physical coupling with the system due to the fact that they're rotating, and whenever we see an imbalance in the load and generation, at the very initial moment, that difference is covered by the kinetic energy, and that then has some impact on the frequency. So we see this inertial response, and control loops are used to replace the inertial response. Whereas in inverter-based resources, we don't have that actual natural coupling with the grid anymore, but this is via power electronics. This has the disadvantage that we don't, again, have this natural coupling, which helps to reduce the speed of the system dynamics. So it's actually a drawback. On the other hand, inverters can also be controlled more freely, so we have a higher degree of freedom, and therefore can also design the controls a bit differently. So the interactions in that case are dominated by the controls. And in that case, actually time constants of the control loops and how they're designed becomes critical, but the time constants are not going to be the focus of this talk. Then let's look at the characteristic of low inertia systems. So at the top, you have a figure which shows the different timescales with first initial inertial response of the system, which then is replaced with the primary frequency control and then secondary frequency control and tertiary. Whereas, as I mentioned, the inverter-based resources now increase the speed of the system dynamics because of if you look at the right-hand side, which is the swing equation with M being including the inertia constant, then if we're assuming that we don't have any inertia, so you can actually introduce some virtual inertia control into the inverter-based systems. If we're assuming that we're not doing that, then we have naturally a faster reaction of the system. So on the other hand, again, they can react quite fast, and that's why we have this blue block here, which gives the opportunity for fast frequency control using converter interfaced generation. In terms of system reaction, if we decrease the inertia, which is reflected in M, and again, here I'm talking about the natural inertia and not imposing any specific controls for the inverters, then we do expect to see an increase in the rate of change of frequency, so faster system dynamics, and also an increase in the nadir, which is the minimum or maximum frequency deviation. Now, before I get into the work, I want to mention that what I'm going to present is done by many different people. contributors. I'm not going to go through the entire list, but it includes former master and PhD students, postdocs of my group, current PhD students, master students, as well as some colleagues, which I'm sure you recognize some of the names. And yeah, so big thanks. And I actually have Ognian also online. He can answer any questions that I cannot later on. Okay, so very good. Then let's go to the first topic, which is dynamic system modeling. As I said, we need the models also in the later parts of the presentation, and I want to use that as a basis. So when we think about system model, and here I really talk about the system model that we will use to derive some constraints that we include in unit commitment or the optimization problem. So we want to have a simplified model. The actual simulations were done with a high fidelity model, with higher order model. So this is really just to derive the constraints and the model used in, for example, the model predictive control approach. I guess the synchronous machine part is rather standard. So that's from literature, where we use aggregate inertia and damping to model the generator dynamics that we have at the top here, aggregating it from the various synchronous generators that we have in the system. And then we have turbine end governor control with turbine time constants, frequency droop factor, some power gain factor, and F is the fraction of total power generated. So this is a simplified system or model of power system with synchronous machines. Now, if we're adding converters to the system, we can distinguish between the ones that actually have an impact on frequencies or grid forming converters versus just grid following. The ones that are grid forming, we're looking at droop and virtual synchronous machines control. So droop is a standard droop control, and VSM corresponds to enabling or using the power electronics in a way that we control it, that it behaves similar to a synchronous machine. And that's what we have on the bottom. So we have converters that have droop control, where we have some gain factor, speed droop, and the time constants of the converter. And other converters include then such which are controlled via virtual synchronous machine approaches. Now, having this entire model, what we can do is derive a general transfer function. And I'm not going to go through the details here, but we can basically add up all of these terms and then get a relationship between the frequency and any imbalance in the system. In order to simplify this transfer function, we're going to assume that the generators all have a similar time constant. So we're going to set TGI equal to T. And then we assume that the time constants for the generators are also significantly larger than for the converters, so setting TC equal to 0. If we're doing that, we can derive this function that you're seeing here in red as the transfer function. And again, we're using that in the following then to derive some constraints. It's not for the purpose of simulating the actual system and running the simulations. What's becoming clear from all of these terms that are defined down here is that the inertia constants, the damping factors, and actually all of the parameters I was showing before have some impact on the behavior of the system, and we can influence it by choosing the control parameters. So we will leverage this function now for deriving a function that gives us in the time domain the frequency evolution given a certain step function in terms of power imbalance. So that's what we have at the top here, again, without providing too many details. Having this function now as a function of time, given a certain step in the delta P electric, we can also derive the frequency nadir. How are we doing this? Well, we can take the derivative of this very first function, set it equal to 0, and identify at which time instances t that function, the derivative is equal to 0. And that tells us when we reach the minimum or maximum value. We have multiple ones because we have an oscillating system. So we have more extrema. And the first one would then be the frequency nadir. And we can plug that into this function. And with that, we have maybe a somewhat complicated expression for the frequency nadir, but we have an analytic expression. In terms of Rocoff, what we can model it as is, well, taking the derivative again of this function here, and then plugging t equal to 0 in, because that's when we're going to see the maximum rate of change of frequency. And then we can also derive the steady state frequency deviation. So we now have these equations, and what it becomes clear looking at these expressions is that it's dependent on the total inertia and damping constants, which can be regulated or influenced via the Drup and the VSM control gains. So having now introduced these equations that I will come back a little bit later as well, we can now look at unit commitment in low inertia system. And the point that I want to make with this part of the work is that we can include constraints on frequency measure. And there's also actually other people have been working on this. How can we include frequency constraints in unit commitment problem? Why is this important? Because if we do have an increased level of inverter-based resources in the system, then we need to make sure that we still have an acceptable frequency in the system in terms of limiting the Rocoff, the nadir, and the steady state frequency deviation, given a specific step change. So we have these functions that I've been using or deriving previously. And what we now want to do is include that in a unit commitment problem. Now, introducing these adds quite a lot of complexity. So what we can do to simplify the frequency nadir equation is using a so-called bound extraction mechanism, which transforms the first constraint into simplified limitations on the different parameters that we have in the system. How we do this is we're just running all possible combinations in terms of unit commitment after a particular generation outage, and then identify for which combinations the nadir is violated. And from that, we can identify these limitations. So we include these constraints in a unit commitment problem. I know there's also been some work on using like linearized approaches and so on. So we've been using this bound extraction technique. Now, if we're talking about introducing renewable generation into the unit commitment problem, we also need to talk about uncertainties. And uncertainties come from contingencies, so generation outages, we're excluding line outages, renewable generation as uncertainties, and we're modeling this with a scenario tree, and each scenario has a specific contingency and a specific scenario of the wind power could also be solar output, but here it's wind power output. I'm not going to talk about how we decide on these wind scenarios. You can use like reduction techniques to get representative wind scenarios. So how do we now do the problem formulation? Well, the objective function includes the minimization of day-ahead energy and real-time balancing cost. And day-ahead energy costs include startup cost, shutdown cost of generators, the actual power output cost, and then for each scenario also the required reserves that we need in order to balance the system. And then the worst case, we have some load shedding. The constraints are the nodal power balance, including also the deviations for each scenario. So we have a power balance for each of the scenarios, line flow constraints, ramping constraints, and power limits, startup, shutdown constraints, and minimum online and offline times for the synchronous generators. And then as an additional part, the limits on Rocoff, frequency nadir, and steady state frequency deviation, and reflected the frequency nadir with these specific limits on the overall parameters of the system. So we can look at some simulations, and we've been working with this 96, a modified RTS 96 bus system. And we're specifically looking at specific contingencies, namely failures of generators at 4 different, I think it was actually 5 different buses. I think I forgot one. Looking at these types of contingencies at the particular hour. So we're assuming that we're just taking into account the worst case in which well, actually the highest wind penetration is present and low demand, which is in our system. We will see that in a second at hour 67. We have 10 representative wind scenarios, so this multiplies then with the number of contingencies in order to get to the overall scenario count. 6 out of the total 16 wind farms are assumed to be operating in grid forming mode, 4 with virtual synchronous machine control and 2 with troop control. The parameters, however, are tuned and given in the unit commitment problem. So and let's look at the results. What you're seeing here is the output from the optimization problem, the power output. First in black, the load, and in blue, the wind generation. In yellow, the output from the synchronous machines without including the frequency constraints, and in red, including the frequency constraints. And in terms of total generation output, there's from the synchronous machines, there's not too much of a difference. Actually, we don't see much of a difference except for where it's zoomed in. The difference in that generation output is then made up by curtailment from wind generation. That's actually not shown in this figure. However, if you look at which generation resources are committed and how many and what they're producing, that significantly changes if we're including the frequency constraints or if we don't. So on the bottom, you see the number of dispatched synchronous generators, which for this simple system actually changes significantly. So with frequency constraints, we have many more units committed that all have to operate at their minimum power output. And the other generators actually have to scale down a little bit in terms of power output to compensate for that. But they are really just present in order to make sure that if one of these contingencies happens at hour 67, that the frequency constraints can be fulfilled. We can now look at what does that now look like if we indeed have a disturbance. Can't remember which outage it actually is. It's one of these generator outages, and what happens depending on the committed units. And we can see that with the frequency constraint, we actually are keeping the limit, or keep the nadir as well as Rockoff limited compared to if we do not include the frequency constraints. We can also look at the costs that we're evaluating it for or showing it for day 3, because the first 2 days, there's quite a lot of startup and shutdown costs because first need to initialize the system. So looking at the costs on day 3, where we also include these contingencies, we're going to see a significant increase in the costs, particularly in terms of percentage, in terms of the startup cost, because we need to start up more units, and in terms also of the reserves in order to keep the frequencies within the limitations. So this is just a toy system, and I think it's some food for thought about what it means if we also have to take into account that now the frequency behavior changes significantly if we have more inverter-based resources in the system. So with that, I'm coming to the second part. As Vladimir mentioned at the beginning, if there's any questions in between, feel free to interrupt me. I'll, of course, also happy to answer questions at the very end. Now, the second topic now focuses on storage sizing for fast frequency control. So the problem statement here is that we can use batteries for fast frequency control. However, they have limitations on power as well as energy capacity. And usually one assumes, well, I have a specific battery with specific power and energy capacity. And then I look at, well, how do I do now the controls for that battery? What we want to do in this project, and that was actually also, I think it was a master's thesis project advised by a PhD student, is to compute the minimum storage capacity sufficient for providing adequate frequency support in low inertia systems. So we're again including constraints on the frequency to determine what is the minimum power and energy capacity that need to be put in place for the storage. Now, the storage is interfaced to the grid through a fully controllable VSC, and we're assuming that we're employing a virtual synchronous machine control scheme. So what that means is when we're doing the optimization for the design of the storage device, we also include the VSM parameters as optimization variables. So we're also determining the M and the D virtual inertia and virtual damping of the synchronous of the virtual synchronous machine scheme. We also assume that the storage device has a given power to energy ratio, eta. So we only need to determine one of these, and then the other one is given, but of course both show up in the optimization problem. Now, just for a reminder and some preliminaries, we work with these equations that I've been showing earlier to include them in the optimization problem. Now, if we just include them, and I mean, what we're seeing from these constraints is that they are dependent on the aggregate damping and inertia. And we have impact on this via the tuning of the storage device. So if we're looking at the system, what could now happen is if we have end up with an underdamped, with actually an overdamped system, then what we end up with is ending up with omega D that is complex, and then having a time which is complex. So that doesn't really make sense. So we're going to make the assumption that we want to have an underdamped situation. And so that Tm is greater than 0 and omega D is a real value, so that we actually do have a frequency nadir that we can compute. So we enforce that the overall system damping, zeta, is smaller than 1, and we have an expression for that from one of the earlier slides, and that the time instance of the nadir has to be greater than 0. From this, and again, I'm not giving details for this, but from each of these constraints, we can derive a specific constraint on the aggregate damping D as a function of the inertia, aggregate inertia M. So we end up with expressions like this here. The Tm greater than 0 leads to a lower bound and zeta to an upper bound. We can plot this also in the two-dimensional plane with the D and M as the axes, what you see on the bottom right. So the black curves are the limitations given by enforcing these two constraints, but then also enforcing the other two constraints can be plotted into this. And then the feasible region is, in fact, the gray part. So then let's look at the optimization problem. So I want to minimize the required storage, minimizing the cost of the storage. I have constraints on the frequency as a function of system parameters and disturbance. So these, what you see on the left, so delta F max is actually a function of the system parameters and the disturbance as I was showing on the previous slide. Then additionally, I include these limitations here to ensure that we do have valid values for D and M. Then I have some non-negativity constraints, such as that the M, which is a tuning parameter, so the virtual inertia of the battery is greater than 0. And then I also have some power constraint on the battery. This is derived from the virtual swing equation, because we're operating the storage as a virtual synchronous machine. So we have some limitations on the power, or that gives us the minimum amount of power capacity that we need. And then also energy constraint. So we integrate this power over time until steady state, and that gives us the energy value. And as I said, we're enforcing a fixed relationship between the energy and the power, and we can vary this eta value for sensitivity analysis. What makes this problem complicated are these two constraints here. And I'm now going to show how we simplify that to be able to solve the problem. So the first one is the approximation of the power constraint. And what we do is we take the left-hand side of this constraint and split it into the two terms, referring to the frequency-related and the Rogoff related power injection. And then we want to conservatively bound it using a triangular inequality, which leads to a conservative bound. And that's what you're seeing here on the slide. Having previously obtained analytic expressions for Nadir and for Nadir and Rokov, this is now a function of the system parameters and the delta P that I assume as a maximum disturbance in the system. For the energy constraint, what I would ideally be able to do is to integrate over this continuous function. But that's not actually doable within the optimization problem. So what we can do is we approximate the signal with 4 linear functions. What we need in order to generate these linear functions is just the input values for the limitations on the Rokov, on the frequency nadir and the steady state. So the maximum values that we include in the constraint. And then we're going to assume that we're working with a system that will indeed reach these maximum values. So what I can then do is, for example, set K1, this value for the linearization, equal to the frequency nadir value. And I can also assume that it reaches maximum Rokov at the starting point, which then gives me a clearly defined first line, and I can derive the time TP. Tm values are derived from this taking derivative of the function for the frequency and setting it equal to 0. And so I get the 2 first maximum values. And I can linearize, therefore, the function like this. It might not be very accurate if the system does not actually reach the nadir or the maximum Rokov, but I will talk about that in a minute. So that's the second part here. The first part is the Rokov part, and there it works in a similar fashion. Here we're trying not to approximate the signal, but actually the energy content of that, so the integral of it, but it works in a similar fashion. So now what's important is to look at, is that now really a conservative approximation or not? And we can verify that for a highly underdamped system. We do it again for like a theoretical worst case scenario, which is a highly underdamped system, which reaches the frequency nadir. So an example is what you have here on the slide, where we reach this nadir and then we have these oscillations. So the gray area is the energy content that we would estimate if we use the linearized approach. And red is at the places where we overestimate the energy content, and purple is where we would underestimate it. And if we're looking at this figure from the fact that we have decaying oscillations, we can conclude that with the gray area, we will overestimate the energy content, which is good because I don't want to get a too low energy content. However, it's possible that, as I mentioned, the approximation is not very good. Like, for example, on the previous slide here, it's not reaching the nadir value. So what we can do is use an iterative approach where I first linearize it using the limitations that are given as an input. Then I solve the optimization problem. I get the optimal values for P, M, and D, so my optimization variables. Having this, I can simulate the system and identify, well, what is now actually the nadir given the maximum disturbance that I'm considering, what is the Rokov, and then use these values to update the linearization. So I'm basically look back at how does the actual curve look like, and then I update the linearization based on this. And with this, I'm going to get a better approximation of the energy needed. There's some additional not so important steps where we do also evaluate what is then the actual energy content and then adjust the values in the second curve here, the linearization a little bit in order to get even closer to the correct value. And we can do this in an iterative way. So then let's look at some simulations. So we have a test system with one synchronous generator and 5 converters, assuming in grid following mode. So the only grid forming is from the storage device. And we assume that that is placed with one of the inverters. The inputs are the maximum disturbance that we expect, the power to energy ratio, and the speed group of the one synchronous machine. Again, this is a toy system just to understand the relationships and the implications of the different assumptions. And there's quite a lot of results shown in this graph here. I am not going to go into details. What I want to illustrate with this is that the inputs heavily impact the nature of the problem. So if we look at the maximum power, what is the maximum disturbance, what is the speed group of the synchronous machine that I have in the system, that can lead to a problem that is too relaxed. So the synchronous machine can basically do the job, or a problem which is infeasible, or different constraints become binding. So this figure shows when which constraint becomes binding. Again, the main point here is really that the inputs heavily impact the nature of the problem, therefore also the solution. Then let's look at the specific case, namely delta P of 620 megawatt, which is of course a large change, but again, we just want to study the implications of the result from the optimization problem. So, and we're assuming we're looking at for two different speed group values, 2.6% and 4.6%. And then what we run the simulation with is without the iterative improvement, where we have some inaccuracies in the estimation of the energy content, and with the iterative improvement. And what you see here are the inputs. So eta is the input, and the speed groups are an input. And what we can see is that for R equal to 4.6%, there's a noticeable threshold in eta after which the additional energy capacity does not contribute anything anymore. So it's really the P which is becoming the binding term. And in fact, because we're talking about fast frequency control, it's only very limited energy is in fact needed. And so what I also want to point out is if we use the iterative improvement, and that's going from the left to the right-hand side, we, particularly in the case of 4.6% for the speed group, we see a clear difference. And that's because in that case, when we have R equal to 4.6%, the approximation with our linearized approach is not very good initially. So we update it and then get a better solution, which reduces the amount of energy that is needed, so the energy capacity. For the case with R equal to 2.6, there it doesn't make a difference because the approximation is actually pretty good. And we can also look at this in terms of the time domain, looking at two different scenarios, which are picked out of these red lines. Specifically, we look at a scenario where we have the speed group equal to 4.6%, eta being 10 seconds. Again, we're talking about very small storage amounts. And then the RG equal to 2.6% and eta equal to 15 seconds. The results are shown on the right-hand side. So in the first scenario, if we do look at the frequency behavior over time, then we see that actually the integral approximation is very conservative because the limiting factor in this case is the steady state frequency constraint. Whereas in the second scenario, which is the one with R equal to 2.6%, the nadir and Drokov impose tight constraints, and the integral approximation is in that case less conservative, and we don't need the iterative approach to improve the storage sizing. So with that, I'm already coming to the last part, which is switching gears a little bit into a different time scale. Well, we're still talking about fast frequency control, but now really looking at how could we do the control design for fast frequency control. So what do I mean with fast frequency control or fast frequency reserves? Well, we know that initially we're going to have the inertial response from the synchronous machines. And then once we have some frequency deviation, primary frequency control kicks in. But before that, we could have fast frequency control given from some inverter-based resources because they're capable of acting very quickly. And we now want to use grid forming inverter-based resources for such fast frequency reserves, but we want to only use it in emergency cases. And I will show in a minute what I mean with this, or how we're setting it up. But we're going to compare two different cases, centralized model predictive control approach and reinforcement learning approach. So for the model of in order to do the reinforcement learning, we need a model, and actually I'm getting to the training model a little bit later, but I first want to explain the control layers that we're going to assume. So we have a two-level VSC control structure. We have the local control layer. We're assuming that it is controlled via speed drop control, and that's what you're seeing here for frequency and the voltage. That determines the set points, and then that's given to the inner loops, which again is out of scope of this presentation, but it's basically a cascade of the voltage and current controllers that then determine this voltage, and then we have the internal mechanisms of the inverter. Additionally, what the focus is now is designing a supervisor controller that adjusts the power output that is given as a set point. So basically adjusting this P by a delta P, but only in response to large disturbances. So we only activate it in case there is a danger that the frequency is violates some constraints. We're going to assume a centralized controller where we have a centralized single agent control structure for emergency activation. We have a number of VSC units that participate in the fast frequency control provision. We assume bidirectional communication to each VSC and unidirectional communication lines for each synchronous generator. And we assume that we're going to have optical fiber with delay below 100 milliseconds. So we're just going to look at what can we achieve in this setup. Of course, that's not how the infrastructure looks like now, but what we could achieve with this. Now let's come to the learning-based approach, and I'm not going to get into the specifics of how the learning approach works, but in general, what we need is a model of the agent-environment interaction, and we have decision variables, which are the adjustments for the power settings for the converter. And as an input, we have the frequencies and the derivative of the frequencies. The derivative of the frequencies, we're using, I think it's 3 time steps in the past, and basically look at the averaged derivative for the frequency at the different nodes in the system. Now, the goal is to keep the frequency in the system after disturbance within permissible limits, but also make sure that we don't enforce too much of a reaction on the inverters. So we want to minimize A, and we also put a penalty onto this reward function. So actually added to this reward function if the frequency violates the frequency limitations, and or if it violates the derivative limitations. And we're using a deep deterministic policy gradient to get the model for the Q function, which tells us what is the expected reward over time given a certain state and a certain decision or action in the system. Okay? So that's the overall setup. We need a training environment for the learning-based approach. Here we're using a second-order VSC model, which includes the active power controller dynamics, a third-order synchronous machine model. And again, this is the model that we're using just for the training environment. Afterwards, for the simulations, it's a significantly higher order model with which we basically demonstrate the performance. The grid model is a DC power flow model, and with this you get the overall system down here, where we have the VSC, which has a speed drop control. We have the system model with the DC power flow and the synchronous machines. We can derive for this the state space representation, and then use that again as the training environment. And we want to get again the relationship between what decisions or what adjustments in the set points for the converters should be made given a certain disturbance in the system. Before talking about how the training works, or talking about actually the test case, let me give you the equivalent M.Sc formulation. And that's what you have on the right-hand side. So we can leverage the same model that I was just showing. So this model here to write down an M.Sc formulation. So this gives us the dynamics, and we want to make sure that the frequency stays within the limits, and we minimize the reaction that is required from the adjustments in the converters. The optimization problem is solved at each time step, and that's set to 250 milliseconds, and then solved, and then actions are applied. In terms of because we need predictions for the power output, we basically assume that the power output change, or the loads, the disturbance stays constant over the horizon. So that's actually the input. In this M.Sc approach, again, this is really just used as a benchmark here. We assume that we have delta P measurements at every single node, which again, it's really just used as a benchmark. In the reinforcement learning approach, we don't need these measurements. And then we have the power output, the set points as inputs, and the measured frequency also as inputs to the M.Sc formulation. Then as outputs, we have the set point change for every converter, delta Pi. So let's look now at the comparison between the reinforcement learning approach and the M.Sc approach. We're using a test case of the IEEE 14 bus test system. We have two VSEs that participate in fast frequency control. We use a high fidelity DAE model for the time domain simulation. And we want to keep the frequency between a threshold of 0.5 Hertz and the rock-off in threshold of plus minus 1 Hertz per second. Now, first, we need to do the training for the learning-based approach. How that works is we introduce random step disturbances. Step disturbances correspond to delta P values, so changes be it in the load or the generators at particular location. And each episode corresponds to one of these changes in the disturbances. And for each episode, we test different actions and then learn what is the result in terms of frequency, and then basically learn from this. So basically explaining this in a somewhat simplistic way. The learning process, what we're seeing on the right, is actually converging for the different parts in this, the reward function, the loss function. And what you're the reason why I added this figure here is that at episode 10,000, what we're doing is we're also testing will it be able to adapt to changes in the environment. And what happens here is that I believe it's some of the inertia constants of the machines are changed, and that changes the overall environment, but it adapts rather quickly to such a change. Now, the first step in the simulation is to do some testing of the agent. So is it able to adhere to the frequency limitations? So we add 800 megawatt disturbance at one of the nodes and then see what happens in the system. And what you're seeing on the right-hand side is the frequency, the derivative of the frequency, and the steps that are enforced at the converters via the supervisory controller. So it realizes that it will violate the frequency constraints if there's no reaction from the converters. And one can see that we keep the frequency and the derivative of the frequency within its given limits. Then finally, a test case where we compare it with the model predictive control approach. So we introduce 1,000 megawatt disturbance at the bus 14. And on the left-hand side, you see the results for the reinforcement learning approach, for the right-hand side for the M.Sc approach. The dashed curve are if we don't use the supervisory controller, so really just the droop controller, and we can see that it violates the frequency limitation. Now, if we compare the two, well, what I should say is that I mentioned earlier that the M.Sc updates the delta P every 250 milliseconds. This is due to the fact that it does take some time to compute, and we're taking that into account. And then also we have some time delay in the communication. So delta T is 250 milliseconds. For the RL approach, we're much faster in determining the required delta P, and so it needs a lower time step, which we set to the time delay of the communication, so 100 milliseconds. And from the results, what we can see is multiple things. One is we have a smoother response from the learning approach. This is due to the fact that we can update more frequently. And as a consequence also, and this is a consequence again of the shorter operating time steps. If we would do the M.Sc also with these smaller time steps, you would get rather similar curves. But the point is that in the reinforcement learning approach, we don't need to measure all of the delta P across or estimate all of the delta P across the system. So that's the advantage of the RL approach. And what we also see is that we have some oscillations in the delta P. So the dash curve are again only droop control, and dash curve plus these controls down here give us the curves at the top. So that's the you can see that we have a smoother response for the RL approach. With that, I'm coming to the end. So I was showing you 3 different optimization-based problems, some of it really with the idea of showing you what are the implications of having more inverters in the system. Overall, we can say that the characteristics, including the dynamics of the power system, are changing due to the ongoing energy transition. Inverter-based systems do offer new control capabilities, but of course also have some negative effects. So they are the cause for faster system dynamics. Then availability of natural and virtual inertia will likely have to be considered in the unit commitment, and also the control capabilities. Storage is suitable for fast frequency control. In fact, we ended up with having small energy amounts that we need. Even though we need to define this capacity and also the power in correlation with the control settings for these devices. So they need to be defined such that sufficient energy is available and sufficient power capacity is available. And finally, the variety of control mechanisms for fast frequency reserves provision by inverter-based resources are possible. I was really just showing 2. There's a bunch of people working on this as well, with proposing different ways of enabling these. And then finally, the references where you do find the work that I was just presenting. And again, thanks to all of the co-authors and particularly the students who did all of the work that I had the pleasure to present today. So with that, I hope I wasn't overrunning you with too many topics, and I'm open for questions.
Thank you very much, Gabriela. It's a wonderful presentation. So now we have roughly 10 minutes to ask questions. So please feel free to unmute yourself, raise your hand, or drop questions to the chat. And I'll repeat them. And maybe now, as we're waiting for the questions to arrive, I can ask first question. Gabriela, I was thinking in the first part of your presentation, I learned that you spent a lot of time in analytic derivation of some tractable Nadir expression for intermittent problem. And I was curious, when it comes to like a large systems, right, you might have some errors in the data. For example, time constant might be slightly changing over time, right? So I was actually thinking, can you use some data-driven techniques to estimate this frequency as some, I don't know, linear function for your unit commitment problem?
Yes, I'm sure there is. I mean, you saw in the last part, we've been considering, of course, learning approaches for a different problem, of course, but I assume that you probably can learn. I mean, when we using the bound extraction, it's a simplistic way of doing a data-based approach where we run a lot of different simulations and figure out which one are lead to valid frequency behavior and which ones don't. So yes, could be also an option with the analytic expression. I agree. I mean, you're going to have some impact of the different system parameters if the system changes or errors in it. But on the other hand, you really have a physics-based analytic expression that allow you to, again, base it on the physics, as opposed to if things change in the system, then you also need to rerun, I guess, the entire learning again.
Yeah, makes perfect sense. Thank you. Thank you. So we have a question from Danilo. Please feel free to unmute yourself, ask your question.
Hello, everyone. Hi, Gabriela, and thank you for the very nice presentation. I'm doing a PhD in a similar topic in ETH Stockholm and now in MIT. I have a lot of questions, but maybe I will just repeat myself to two. The first one is related to if I notice correctly, you neglect the voltage dynamic in the system or the impact of load that would have on frequency stability. So what is your takeaway on that?
It depends. So we're neglecting it in the derivation of the expressions for the constraints and for the learning environment. But the models that are being used to simulate the system, they include, I don't know how order the order of the system, but do include really the details of the synchronous machine as well as of the converters. I don't know if Ognian can comment on the actual simulation environment as he has been using this.
And then do you see some difference in the location from where you provide the frequency support, depending on the amount of load or the type of load which you have in your system?
Yes, I mean, that has been also a part of other work looking at the location and the impact of the location. And yes, the location does have an impact. That is true. Yeah.
Yeah. I mean, that was an interesting point for me because I'm now investigating on that. And also just another question related to more pragmatical point is that, I mean, system operators have some practice that they impose specific requirements towards the units that want to participate in frequency control. And that is fixed. They require some amount of power within specific seconds. Within 5 seconds, they require, I don't know, 50% of power or something like that. It seems like from the problem you presented, inverter-based unit could compensate for generators if they're too slow.
Yes.
And then how do you see now, how would you impose the new requirements in the future towards the units? How would you say towards some generators, okay, now you need to provide this much, or you need to follow the control of inverters. And if you don't have inverters, you have to be better, and so on. How would you do that?
Well, that's a good question. I haven't really thought about it.
Because I think, for example, in the Nordic countries, we have Vattenfall or some other companies. They require for them, okay, you don't know the parameters of your governors of your turbines, and we are not allowed to have this information. This is your thing. So we just tell you, okay, you have to make sure that you provide specific power with a specific amount of time. And now that seems like a bit too conservative because, okay, you require those units which have non-minimum phase effect to remain stable and be fast. You restrict them so much. Then you can just ask from HVDC to provide something more and you're good. So then what do you do in these cases? How do you tackle this on a daily basis or like season-based? How do you impose these requirements?
I mean, you're right that the synchronous generator or any resource that wants to participate in, be it in any of the frequency services or ancillary services, has to prove that they're capable of fulfilling these. Could imagine that you then essentially have the same thing for fast frequency. I mean, it doesn't have to be actually inverter-based resources, but they're suitable because they can react quickly. So if another resource can qualify for that type of service, but then you would have to also impose the constraints or regulations on who can provide these fast resources. So that's probably how it will work. How if that would have implications on the slower ancillary services, I don't know if they would have to be redesigned in terms of the capabilities they need to have. But I mean, there's various countries which do look into who do look into or have implemented faster than primary frequency reserves. And I'm pretty sure they probably also have some requirements for what these resources have to provide.
Yeah, I think it's just going to be how to differentiate these requirements among different units.
Exactly.
Thank you, Mike. Thank you very much for the.
Thank you.
Thank you, Daniela, for a question. We also have a question from Akhilesh.
Yeah. Hello, ma'am. I have a couple of questions, but I'll just limit with respect to the time. So the one question that I have is related to the optimization related to the scheduling problem, in which you consider the scheduling of the generators for maintaining the critical level of inertia in the system. How do you see the applications of the inertia provision from the converter-based sources? And considering that, how do you see this problem as a day-ahead market problem compared to the real-time market problem?
Okay, so the problem I was showing you with the unit commitment was basically, I didn't explicitly say it, but also one of the conclusions is that, well, maybe you should think about how you can also leverage converter-based resource. There, in that simulation, I believe we, if I remember right, we fixed the control parameters from a number of resources, and it wasn't inherent in the optimization problem, but that's certainly something to study and important, because if you do have these resources that can provide it, then sure, why make sure that it's given by the synchronous machines if you have other resources that can provide the same services. The question, however, is, I mean, we're talking about the resources providing the service that actually caused the issue. So how do you then make sure that you do have resources available? In that case, it might have to be storage or whatnot, or loads. I mean, loads could also be providing these fast services.
Okay, so one last thing regarding the frequency constraint that you have, which you have modeled as a slope parameter, which is the disturbance to the kinetic energy ratio of the system, delta P by M. So by doing the optimization of the scheduling problem, it is possible to have a scheduling, like different scheduling with respect to the iteration of the optimization itself. So within that, how you are keeping the value of a delta P as a constant, because the constant is depending upon the disturbance size, which may get changed depending upon the schedule.
Yeah, so it basically looks at what is the maximum potential disturbance, and then you're basing it on that. So it's basically the worst case scenario. So the delta P is an input into the problem formulation, and yeah, that again, that's heavily dependent on the situation. But if you're capable of limiting it the largest disturbance, then you can also of course, location plays a role and so on, but yeah, approximately you can say that then should be also fine for other disturbances.
Makes perfect sense. Thank you so much. We just need to accommodate one more question from Chu. Thank you so much for your questions. Yeah.
Hello, everyone.
Hello.
Yeah, thank you, Professor Hug. A very interesting presentation. This is Chungda from Imperial College of India. Yeah, I have just a few quick questions. First, can you go to the power constraint in the storage optimization?
So this one, which slide do you mean?
Like the power constraint where you have like the magnitude of roll-off times. Yeah, this one. So basically you are using the maximum of the rock-off and the maximum of the damping times the frequency deviation.
You mean this up here, right?
Yeah, this constraint.
Yes.
So
just to be clear, maximum means the maximum that it's observed in the system.
Yeah.
It's not the limit that we're setting.
Okay.
And
But
so this is a function of the variables.
Yeah, but I just wondering, this two value may not be attained at the same time, right?
That is correct. So
Yeah.
f dot max is at t equal to 0, but still the PB that you need would still be a function of this.
Yeah, but I just wonder, would this be like a little more
okay. Now I see your
conservative?
point.
Yeah.
That's correct. Yes. Now I see your point. Yes, you're right. You would. It is a conservative approximation. I mean, even the fact that we're using this basically a triangular approximation is an approximation. So yes, in general, both constraints are conservative constraints. So we want to make sure that we do have enough capacity. You of course shouldn't be over conservative, and that's what we're showing then also in the time domain simulations.
Okay. Yeah, and like another question for the reinforcement learning based. Yeah. So here I'm wondering. So since the RL is kind of non-parametric controller, so I'm wondering, why do you still like preserve the Druck structure when designing the reinforcement learning control?
I'm not sure I understand the
maybe can you go back to the first page? Yeah. No.
This one here?
Yeah, this one. So here, basically, you are at a new reference delta P C star, right? Mm-hmm. Within the Druck control of the converter. So I'm wondering, since you are using the reinforcement learning control, can you just like directly design the output power? So instead of preserving this Druck-based control structure.
Well, what we're doing is we're determining a set point, the general, and we're adjusting that set point. But the goal is not to interfere with, if not necessary. So we keep the speed droop, and therefore how you can then still have an adjustment of or an impact of the supervisory controller is by adjusting the set point for the speed droop.
Okay.
All right. I guess we can pause here. So thank you everyone for your very insightful question. We're just a little bit over time, so and not all of us can stay longer. But I just want to thanks once again our speaker Gabriela for today. Thank you. It's a wonderful presentation for the final episode of the series this spring. Yes, it's a pleasure, Gabriela. And just a quick announcement that we pause our series for now for the semester, and we will prepare some updates for you guys. We will communicate through our mailing list. So we will keep you updated on the future of our seminar series. So and for now, I can only wish everyone a good summer break. Yeah, thank you very much for staying with us.
Thank you. Thanks for joining.
Bye.